Coming up on our grand tour of construction calamities, parking in Baltimore becomes a slow-motion catastrophe.
I can remember just seeing the vehicles go down, and they sank in.
A narrow escape for the most famous building error in the book.
The tower began to sway slightly out of control.
And a Manhattan skyscraper with a deadly design flaw.
There could be up to 200,000 fatalities.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, these are the engineering catastrophes that only an expert can hope to fix. When engineering goes wrong, news crews usually arrive after the dust has settled. But when the calamity is caught on camera, we get a unique window into what went wrong. Just like our first catastrophe in Maryland. Here in Baltimore, life on the street got very dangerous in 2014. The neighborhood had been sitting on a ticking time bomb.
When it was ready to go, boom, it just went.
And it hit like a mortar round. Boom!
Baltimore. This grisly old harbor town is nearly 300 years old. Almost a third of its buildings are registered as historic, more than in any other U.S. city.
Baltimore is one of the older cities in the U.S., and there's a lot of structures that were put there at least 100 years ago. And of course, you know, time takes its toll.
This aged Atlantic seaport is always in need of some TLC.
The maintenance of any large city is a massive undertaking.
As the Charles Village community discovered, dramatically, one rainy April day in 2014, residents of East 26th Street noticed that years-old cracks in the road were growing rapidly. Community leader Matt Brady witnessed the event firsthand.
I remember it was raining so hard, this crack right here literally opening up, like peeling an orange.
Next to the railway, beneath the road, was a retaining wall, and it's worth mentioning that this wall is 100 years old.
The old retaining wall supporting 26th Street above the train tracks was beginning to give way.
One of my supervisors in the field came in named Howard. He said, hey, Matt, the street up there on 26th Street is about to give way. I said, what are you talking about? He said, the street. You know, the rain's coming down is causing the street to separate.
By midday, the cracks in East 26th Street were growing wider.
And I remember running over here. It was amazing. And literally, you could stand right here and see this wall leaning. To be quite honest, I was afraid that if a train came through, somebody would die. I began to tell the guys, say, hey, I need you to do me a favor. I need you to take one of the trucks, block this street right here. Make sure no traffic goes down there, because that'll make it worse.
3 hours later, local residents looked on in shock.
Margaret Brent Elementary School is about to let out. And I said, man, we really got to make sure those kids don't get out. So we sent one of our guys over there to talk to the administrator, said, look, don't let the kids out. It's a major emergency. The next thing was to secure the area and to make sure these residents were out of their houses. Now, to stand right here, and I will never forget, to see these cars leaning literally at a 90, almost like this, like a 90-degree angle. And to hear the street crackling like bread. I mean, you can stand here and just listen to the street tear.
When the road starts cracking like that, and you've got this 100-year-old retaining wall, inevitably, it's not going to go well.
A passerby with a camera pushed record just in time.
And I can remember just seeing the vehicles go down, and they sank in, and then like in a matter of moments, we watched that whole side of the street explode. and it hit like a mortar round, like boom.
The collapse was an urban landslide.
When landslides happen, they can be really sudden and dramatic. People in nearby houses thought a train had derailed just by the sound of this. And it brought, 8 cars with it. These things were totaled, just crashing down onto the tracks below.
Amazingly, no one was killed.
You never ever would imagine a million years to witness something like that and to see the pain on so many people's faces, to see people crying. After it collapsed, there was like a deafening silence.
As the dust settled, witnesses wondered what had caused this cataclysmic collapse. The seeds of the disaster were planted more than 100 years ago, when a new railroad was built. This Baltimore neighborhood was at the top of a slope, leading down to the tracks. In 1914, engineers built a 35-foot-high retaining wall to support the road above the railway. It was a massive undertaking. And right from the start, it was subjected to Baltimore's extreme climate and soft geology.
Baltimore is built on clay soil and gets very cold, harsh winters, but also heavy rains. And all of those things combined causes a lot of ground movement.
Baltimore's temperatures fluctuate between scorching summers and freezing winters. As the earth freezes, it expands, then contracts when it thaws.
It's those things that brought the retaining wall to breaking point.
April of 2014 was one of the wettest on record, and by the 30th, the already unstable ground was dangerously waterlogged.
There's no doubt that the heavy rainfall prior to this disaster played a huge role in bringing down the wall.
While the wall did stand up to brutal conditions for a century, in the end, this was a massive fail. The city had a disaster on its hands, with a road destroyed, a railway line buried, and residents forced out of their homes. An engineering rescue was desperately needed, and fast. Baltimore, Maryland. East 26th Street had just collapsed, burying a railroad and leaving homes uninhabitable. A rapid engineering response was needed. Jim Gwinther was the project manager in charge of the repair mission.
About 1:30 in the morning after the incident, and we had everyone evacuated and we had all the utilities turned off. It was probably still raining. And at that point, we understood that we had to break this problem into 4 distinct parts. The emergency response, which was make it safe for the community. While that was going on, we then had to come up with a solution that would allow us to do a temporary fix that allow the residents to get back into place and allow us to then work towards the final solution, which was excavating the material to allow for that construction.
Once Jim's team had cleared the site, they got to work on a new retaining wall to support the road above. To create rock-solid foundations in the soft ground, engineers installed 65 reinforced concrete columns. To improve drainage, they added a layer of sand and gravel. But this wasn't just a physical fix. The rules were changed to ensure this wouldn't happen anywhere else in Baltimore.
If there's a silver lining to this, it's that now there is one department who is responsible for monitoring ground movement and looking at its impact on structures in Baltimore.
With constant high-tech monitoring, city officials can now spot problems developing below ground before they turn into a major disaster.
I think if there's a lesson to be learned here, it's that when you see warning signs like giant cracks in the road or land shifting, it's only a matter of time before something catastrophic happens.
For our next calamity, we head to Italy. And a new twist on the best-known building blooper of all time.
At 800 years old, this is the original engineering mistake.
The Leaning Tower of Pisa is one of the most famous buildings in the world.
Everyone who comes here wonders why it doesn't fall.
But just 30 years ago, engineers came close to destroying it. Pisa in the 12th century was a growing naval power.
The Pisans got rich quickly by raiding Sicily, and they wanted to show the world how important they now were. Centuries later, we still see how important they are, but not quite in the way they wanted.
In 1173, the Pisans started building an ornate bell tower for their cathedral.
No one had built anything so ambitious here, and things started to go wrong very quickly.
As tour guide Chiara Celli explains.
Just a few years since the beginning of the construction, when they reached the 3rd floor, the tower started leaning. And it was not supposed to lean, not at all. So this was a really bad mistake.
The tower was actually sinking on one side. But rather than stopping the construction, they continued to build it taller.
But as the tower was slightly leaning towards one direction, the second architect made the next levels slightly leaning opposite.
Building one side higher than the other is never going to be the best solution. Surely it's a sign that something is wrong. You are just asking for trouble.
Hoping to correct the lean, they even tried adding more steps and taller columns to one side. But the extra weight made things worse.
It seems obvious, but you have to remember that engineering knowledge at that time was nothing like it is today.
Throw in a series of wars, and it took 200 years to get the off-kilter building finished. Finally, in 1372, the tower opened, and it's been leaning ever since.
I can demonstrate with this ball that the tower is inclined, and this is not horizontal.
Ironically, the delays to construction are why it's still standing today. If they had built it any faster, the tower would have certainly toppled because they had made a fundamental error at the start.
What did the original engineers do so wrong that they condemned Pisa's tower to lean? The Leaning Tower of Pisa opened to tourists in 1372. It had already been leaning for more than a century because the engineers messed up right at the start.
This might be the right time to point out that in ancient Greek, Pisa means marshy land.
Author Nicholas Schrady is well versed in Pisa's geology.
Most of the terrain in Pisa is essentially a former bog, a former swamp, and the subsoil in Pisa is extremely shifty and delicate, and it does not withstand heavy loads.
Sandy and soggy ground is definitely not ideal for tall, heavy towers unless they have rock-solid foundations.
And this is the root of Pisa's problem. The tower's foundation is far from solid. The nearly 200-foot-tall tower sits on supports that are less than 10 feet deep and surrounded by soggy ground.
It's like building a tall tower on a sponge. It can only go so high before it's going to start leaning. In fact, it's a miracle it never collapsed.
The tower's tilt was enough to startle onlookers, but crucially, not enough to topple it. The original mistake occurred at the beginning of construction, but the tower survived for centuries. However, just a few decades ago, engineers came very close to bringing the tower to its knees once and for all.
Most of the attempts have failed, and those who most wanted to save the tower are really those who almost contributed to toppling it over. One of the most brutal interventions in the tower was conducted by Mussolini, and that intervention was about as brutal as fascist politics. He had the idea of boring 361 holes in the foundation and pumping it with 90 tons of cement. Mussolini also owned the cement factory, it should be said. The tower began to sway slightly out of control, but it's always managed to stabilize itself.
By 1990, the tower's lean had reached an angle of 5.5 degrees. Officials feared this icon would finally fall, and for the first time ever, it was closed to the public. They had every reason to worry.
Now, lots of ancient buildings, they do lean, but the Leaning Tower of Pisa just looks like it's defying the law of physics. And that's all to do with its centre of mass, which is just about here.
Experts calculate the tower's center of mass is around the 4th floor. As long as this sits above the base of the building, it will stand. But if it moves outside of that area, you have a disaster.
Calculations show that when the tower was at a lean of about 5.44 degrees, it should have collapsed. Now, by 1990, it was already at 5.5. It should have gone down. No one knows why it didn't collapse.
With so many rescue efforts over the centuries, the calculations of the lean have become confusing. To make matters worse, the lean compounds an issue hidden in the walls that could take the tower out before the lean knocks it over.
The greatest danger for the Tower of Pisa has not been that it should simply fall over because of its weight. There are other dangers as well, one of which is the incredible amount of stress which is produced on certain areas of the tower due to the weight of the tower.
The tilt strains the walls, which can be devastating to a structure built from solid stone. But while these look solid, the walls are filled with a random mix of building materials, making them less sturdy.
There has been a great concern that the tower would rather burst and implode rather than topple over.
Not only could the tower have fallen, it could have exploded at any point. It defies belief that it's still standing.
Back in 1990, with the icon threatening to fall, the world's best engineers rushed to save it, with almost catastrophic results.
What they first did was they bored holes down 40 meters into the bedrock and introduced steel cables to stabilize the tower. Now, in order to do that and not have the entire terrain become flooded with water, what they had to do was pump those boreholes with liquid nitrogen.
When you freeze the ground, you're also freezing the water contained within. And when water freezes, it expands.
And when the water thawed, the ground shrunk, causing the tower to rock back and sink as much in one night as in the previous year. Once again, this icon was close to collapse. Could engineers finally save the mighty tower? In the 1990s, engineers attempting to save the Leaning Tower of Pisa realized it was close to collapse. The team secured it with cables to prevent disaster, then went back to the drawing board. They came up with a solution that they hoped would finally stop the building from falling further.
Most solutions tried to help support the structure, but this just put more pressure on the ground underneath, making the problem worse. Eventually, wily engineers let gravity help out.
They had to start basically digging, drilling through into the soil, and they started removing really slowly the sand and a bit of the clay. So they created like a hill of clay nearby here, and then the tower started leaning a little bit less. So it became to lean now, it leans as it used to lean 2 centuries ago.
Digging under the tower turns out to have been a brilliant idea. It reduced the lean by about 10%, which, although that doesn't sound a lot, it brought the tower back from the brink.
It took more than a decade to complete the undermining fix, but in 2001, the tower reopened to the public.
Crucially, the angle was down to 4 degrees, well below the 5.44 limit, enough to prevent a collapse, for now.
But with a landmark this renowned, Nunziante Squeglia from Pisa University is leaving nothing to chance. He's using precision optical sensors to track the smallest changes in the tower's tilt.
This is an optical level. This instrument, we can measure on that scales if there are some movements of the tower. I measure the variation of that points, and from the variation of the elevation of that points, I deduce the rotation of the foundation of the tower.
In a way, the fact that the Tower of Pisa is located in the Campo dei Miracoli, or the Field of Miracles, strikes me as perfectly apt, because the tower should have toppled, in fact, centuries ago, and it hasn't. It goes on standing and will for 300 more years at least, and that, in a way, is a miracle.
Let's hope they're right and the tower continues to lean for hundreds of years, but just not too much.
Now we're heading to New York and a skyscraper that was very nearly blown away.
This blunder sounds too incredible for it actually to be true.
This tower hit a deadly flaw that could have devastated Midtown Manhattan.
There could be up to 200,000 fatalities.
Until a sharp-eyed engineering student saw the storm brewing.
Only luck prevented a genuine catastrophe.
Manhattan, the spiritual home of the skyscraper. In 1977, a high-flying investment bank opened up its headquarters at 601 Lexington Avenue. At 59 stories, the tower was the 7th tallest building in the world.
601 Lexington, at first glance, looks like a typical skyscraper. It's actually this really unique engineering marvel.
The fact that it ever got built in the first place is a little short of a miracle.
Defying skyscraper convention, 601 Lexington is elevated on stilts, 9 stories high. Sitting not at the corners, but midway under each side. And nestling beneath the tower is St. Peter's Church. Construction lawyer Michael Vadaro explains the unusual layout.
When Citicorp purchased the land from the church that sits in the northwest corner, there was a specific mandate that the building could not in any way touch the church. It presented a very difficult scenario for the engineers and architects of the building to figure out how to effectively use the space and yet keep the church separate.
As part of the deal, St. Peter's had to get a brand new church at the exact same location. Avoiding the church was a serious architectural challenge.
With astronomical property prices in Manhattan, they couldn't afford to just use part of the plot. They had to use the whole thing. So the architect came up with a solution that really pushed the boundaries of engineering.
Incredibly, the new skyscraper straddled the church.
The design is ingenious. It avoided the church and it created a unique building. Problem solved, right? Not quite.
Placing stilts under the sides, not the corners, meant they had to rewrite the construction rulebook. Engineer Stephen Ressler explains.
That architectural design created a really unique set of demands on the structural system, and the structural engineer responded in an equally ingenious way. The essence of that structural concept was the inclusion of these V-shaped diagonal braces called chevron braces into the design of the structural system. And what the chevron braces do is pick up a very substantial part of the weight of the structure, which are configured such that they transmit that load diagonally from out here at the corners into the central spine, such that all that weight can then be safely transmitted directly vertically downward through the supercolumns into the building foundations.
Conventional skyscrapers are supported by both vertical and horizontal beams. Switching to chevron braces was the key to using stilts and levitating over the church. When the tower opened in October 1977, thousands of people were soon working in the 59-story giant. All seemed well until June of 1978, when Diane Hartley, an engineering student, discovered an unforeseen danger.
This was such an interesting building. It was really novel. The design was of a type that hadn't ever been done before. And so I attempted to replicate the calculations that the engineer of design would have undertaken.
Although Diane was still a student, what she discovered was astonishing.
She believed the 59-story tower building was at risk of toppling.
According to Diane's calculations, in a strong enough storm, the building would be blown over. And with Hurricane Ella heading for the Big Apple, the race was on to save the tower. .601 Lexington Avenue, with its unique stilts design, is one of Manhattan's iconic skyscrapers. Completed in 1977, the tower pushed engineering boundaries, but a hidden design flaw threatened to destroy it, until Diane Hartley, an engineering student, spotted the danger.
I called the engineers once or twice and got them on the phone and compared some notes, and they convinced me that the building was strong and the building was safe. I accepted their word and so noted in my thesis.
But the team did double-check its calculations and discovered that Diane was right. 601 Lexington Avenue really was at risk of falling down. Shockingly, the tower was under threat from an unforeseen danger: storm winds hitting the corners. Engineers crafted a tower that could take winds up to 70 miles per hour if they hit directly on the sides, but not if those winds hit at the corners. Robert Rattay later worked with the lead engineer and explains why this wasn't factored into the original design.
At that time, the building codes required that the wind loads on a building be calculated on the basis of the wind hitting the building flat on. And that's what they did. And then later on, by the student who did the thesis, it was discovered that actually the wind loads are different when it comes against the corner of the building.
But the risk from corner winds wasn't the only threat. There was another problem, this time with the building materials.
LeMaisure's engineers and the contractor who was responsible for building this structure had actually made a substantial change to the original design while the building construction was underway. And that change was to modify the connections which tied the diagonal braces into the remainder of the structural system from welded connections to bolted connections.
A weld is one piece, so it contains less points of weakness. That's not the case with a bolt that contains many different parts. So a weld will take much greater forces than a bolt.
If all of the computations that were done to document the problems are correct, these connections would have broken. Here, here, here. And these rectangular panels would have distorted into parallelograms, and the entire building would have essentially tilted over and fallen sideways.
Thousands of bank employees and Midtown residents continued with their daily lives, while engineers wrestled with the numbers. Based on the wind calculations and the bolted joints, experts predicted the perfect storm in terms of strength and direction could hit the tower once every 16 years, with catastrophic results.
Now, just a few blocks north and west of here, we have Central Park. But there are a number of buildings and a number of businesses that are located here. And so if you picture this 715-foot tall building toppling over, it would essentially create a domino effect that would take out this entire swath of Manhattan all the way to Central Park. The American Red Cross actually estimated that if that happened, there could be up to 200,000 fatalities.
Diane's warning came in June, and with hurricane season looming, engineers had a strengthening solution by August. To avoid panic, the team kept their work quiet.
So implementing the fix happened at night. During the day, workers would come into the building and work, yet at night, this secretive process of fixing all of the issues of the building was taking place.
I remember having seen more than once these lights, sparks at night. Sometimes people talk about it. You know, when you come into LaGuardia, you have these things. What's happening? Well, what was happening, they were welding at the City Corps building, but nobody knew what it was.
The solution was simple. They welded 2-inch thick plates across each of the building's 200 bolted joints. The 3-month repair job became a race against time. Hurricane Ella was lashing its way up the coast. A massive evacuation was almost ordered, but at the last moment, the hurricane veered away and disaster was averted. The design flaw and subsequent fix went largely unknown for almost 20 years, until in 1995, a New Yorker article made it the stuff of legend.
With such a mammoth mistake, you'd expect the engineer responsible to be in a lot of trouble.
It has become a legend, the way he handled it. He came clean in a very professional and smart way. He not only announced the problem, but he came with a solution.
Diane, the student who saved the day, still reflects on the experience.
So when I think about the fact that my call led to someone after the fact realizing that there was such a critical problem with the building, that if it hadn't been discovered, could have made for a major catastrophe in the city. It's kind of mind-boggling, and it makes you feel very humble.
This was a catastrophe waiting to happen, and until Diane warned them, nobody knew anything about it.
When you're attempting something that's never been done before, even the biggest brains will get it wrong sometimes.
Now we head to London, England, and a bridge that made headlines for all the wrong reasons. Bridges have been built across the Thames for centuries.
London is famous for its bridges. By my count, there are more than 30, some over 200 years old.
But 20 years ago, a new iconic bridge left pedestrians with a very queasy feeling.
It was a fundamental design flaw that even the biggest engineering brains overlooked.
With the year 2000 approaching, London was looking for a flagship project to mark the arrival of the 21st century. The winner was the aptly named Millennium Bridge, a unique pedestrian-only crossing spanning the Thames. Roger Risdell Smith was part of the design team.
We came up with the idea of this being a blade of light because we wanted it to be a slim, very, very thin structure. We wanted something that when you stood on the bridge, you would have an unimpeded view all around you because there would be no structure that would come up above your sight line.
Engineers went with a modern take on a classic bridge design.
The Millennium Bridge may look different, There's actually a suspension bridge, like the Golden Gate Bridge in San Francisco. However, this is a lateral suspension bridge. Instead of the weight being supported by wires from above, they're tethered to supports on the side.
There were none of the columns or cables that would have ruined people's views of the River Thames.
You can see why this bridge was chosen. The design was absolute cutting edge, and even 20 years later, it still looks so beautiful.
The Millennium Bridge opened to the public on June 10th, 2000. But things didn't go as planned, as it started to sway dramatically.
It was around about 50 to 60 millimeters movement in each direction. So a total of about 100 to 120 millimeters movement. It wasn't continuous. It would happen for a little bit of time, and then it would stop again, perhaps 30 seconds, perhaps a minute, and then it would stop again. But nonetheless, it was an effect that we could feel, and it was something where we were looking at it and we were thinking, what's going on?
All bridges undergo some sort of movement or flexibility. It is built into the design, but this kind of movement would seriously worry.
The more people that crossed the bridge, the more it swayed.
When the bridge opened, it became very, very crowded. In fact, we calculated afterwards that around 100,000 people crossed the bridge on that first Saturday.
Just 2 days after opening, amid fears of injury, they were forced to close the bridge.
Spotting the failure so soon after it opened made headlines around the world.
With the eyes of the world on them, the project's lead engineers had to figure out why their bridge was swaying, and fast. The year 2000, London's Millennium Bridge had just been unveiled to the public. However, a swaying bridge was not what the designers had in mind. The cause was something they hadn't predicted. A perfect storm of physics and engineering, triggered by crowd dynamics. Professor Wanda Lewis is an expert in bridge design.
The people on the bridge, when they walk on a bridge, they don't walk in straight line like on the catwalk, models like that. We tend to walk like so. So there's going to be a certain angle to the force exerted on the deck. So there's going to be a predominant vertical force and very tiny lateral force. When you've got thousands of people on the bridge, each exerting this small lateral force, that was enough to put the bridge into lateral sway.
The crowds walking in time, side to side, caused the initial sway, but this in turn triggered another issue, a result of the bridge's radical design. With cables running alongside the bridge instead of suspended from above, they had to be extremely tight, and as the bridge swayed, they vibrated.
There was sufficient number of people to excite these cables, which are basically like guitar strings being plugged.
If you pluck a guitar string, it vibrates at a certain note. All structures are the same. If they are hit with a force, they vibrate at a certain frequency. That's called resonance.
Resonance can be extremely destructive. Although there was no structural risk to the Millennium Bridge, this same force was at the heart of the swaying. The vibration caused by the crowds of marching people settled into a rhythm. By pure coincidence, its resonance closely matched that of the bridge's structure. The two forces working together exaggerated the movement.
When masses of people walked down that bridge, they created a natural frequency, and that frequency matched the natural resonant frequency of the bridge itself. And those combined frequencies created a sway that was out of control.
Resonance has been a factor in bridge design for more than a century. Long ago, Army engineers realized that troops marching in step would shake bridges. But this lateral design had unforeseen consequences. Having identified the problem, the team was desperate to save its reputation and went to work on a fix.
What we did was, through that summer, we carried out a walking test where we walked employees from the companies involved in the design over the bridge, and we measured the effect of the pedestrians as they walked over the bridge, what it did to the bridge.
Guided by the tests, the team devised an ingenious and crucially almost invisible remedy: shock absorbers, also known as dampers.
We came up with a solution having carried out those tests, and that was to install dampers across the whole length of the bridge. And those dampers are like the shock absorbers on your car. They're a compressed cylinder of fluid, and a piston strokes through that fluid, and as it does so, energy is dissipated. And you can see some of them here, just beside the arm, beside the transverse arm, is one of the dampers. And these dampers just move very, very slightly to the very slight movements of the bridge that occur now. And as they move, they absorb the energy from the walkers, and that dissipates the energy and stops the movement from developing and becoming larger.
Adding the dampers was a relatively simple and effective solution to the problem, and it still maintained that design criteria, which was to leave the view of St. Paul's wide open.
In February 2002, we carried out a final crowd test where we organised for 2,000 people, the largest test of its kind done on a bridge, to be walked over the bridge and for the movements to be measured. And we did that. That's a very substantial number of people. We needed to have it it was organised by people who organise football crowds, and they walked the people over the bridge, all 2,000 of them, and the bridge behaved as predicted, and the movements were reduced.
Testing and fixing the bridge took a year and a half. In 2002, it reopened, steady and shake-free.
The south bank of the river now has the Globe, the Tate Modern, and with the bridge as well, that makes this area, which has now become incredibly busy, full of people, both commuters, people going to work, but also tourists and people just visiting. It's become a very, very busy area. It's really transformed.
The engineers must have been so horrified by the swaying of the bridge, but ultimately it led to a great solution, and sometimes failure teaches us so much.